Okay, thank you very much. So this is really two talks concatenated into one because I can't be here next week. The first part deals with methods of measuring sea ice thickness.
Is that being picked up on the microphone all right? Can you hear all right at the back?
Can you hear all right?
Yeah, it's okay? All right, sorry, kid.
Okay. How we measure sea ice thickness distribution, and especially how we, to what extent we can trust the results, because every type of measurement yields something that's not quite what we really want, which is a perfect distribution of shape of the ice bottom, distribution of thickness, and a perfect profile of both the ice bottom and the ice top. We can't get that out of anything. We have to be aware of the limitations of what we measure, and the measurements often involve a lot of work. Then I'll go on to talk about the statistical results which come out of that, and why there's, or we don't quite know why, but there are a couple of extremely good fits to two statistical distributions that sea ice follows, and it's a kind of challenge to theory to understand why that is. So first of all, so I'll talk about how we measure ice thickness, what comes out as the probability density function, and how the distribution of ridges and leads comes out of the data, and then what mathematical forms these fit, and where we really need to understand what's going on. So these are the methods that we have for measuring ice thickness, and all of them have drawbacks. The one that's been used the most is upward-looking sonar, which you can use from submarines, AUVs, from moorings with a moored sonar, or from neutrally buoyant floats. This gives you actually the draft of the ice, which is about almost 90% of the thickness, but it's still not the thickness. So this is a method of measuring ice draft, but it does give you the profile of the ice bottom, which is something you need for statistical studies. Second method is electromagnetic sounding from helicopters, aircraft, or from the ice surface itself. And I see Christian Haas is in the audience here, so I'll leave it to him to describe this method. It's the method which gives you complete thickness, top to bottom, and we have to be aware of certain difficulties that sometimes occur with young ridges, which Christian will tell you about that. This is the method that's used most today over the long distance measurements of ice profiles. Airborne scanning laser gives you the equivalent, but on the ice surface, so you have to make a rather dodgy calculation of what the equivalent density of ice and snow are to convert that freeboard that is given by the airborne laser into a thickness. That's the same sort of rather dodgy calculation you have to do with other methods like cryosat. Then laser or radar satellites, just mentioning those, that there's the former IceSat and the future IceSat, which uses a laser. Cryosat uses radar, and they're measuring freeboard, so we have the same problem of turning freeboard into thickness. They're measuring over a large footprint as well. Inferring from wave spectra, this is from the the dispersion relation of ocean waves in ice. If you can measure that, then that gives you a thickness averaged over long distances. The same thing occurs for measuring thickness from change in the wavelength of ocean waves measured from satellite-borne or airborne SAR, and that works really best for pancake ice. And then the very best method of all, of course, is surface measurements by drilling holes. That's the one that gives you the most accurate data, but is also by far the slowest. So start with submarines. This is submarine measurements of ice thickness started in 1958 with the Nautilus crossing the Arctic Ocean. It was by accident that they measured it because they thought they needed an upward-looking sonar for safety, and they saw it gave these wonderful pictures of the underside of the ice. So this is an early British effort. This is me, and this is the captain of the ship. And the captain became an admiral and I became an emeritus professor. So obviously I chose the wrong profession. So, this is the results that come out of this was early work where you're using a wide beam sonar or relatively wide beam sonar. So the first thing you see when you first look at these profiles is how impressive the pressure ridges are. That this one is about 30 to 40 meters deep. There are ridges that have been measured up to 55 meters deep. But if you look at the mass of ice that's contained in these ridges, it is in fact over the Arctic as a whole, more than half of the mass of sea ice in the Arctic Ocean is contained in the pressure ridges. So they are very remarkable features of the ice and should really deserve to be studied more carefully, because we need to understand how ridges form and also how they decay. But here's a more typical profile, some hefty ridges, thick, rough, multi-year ice, thinner first-year ice, very thin refrozen leads. So that's the landscape of sea ice, and you can immediately see that when you start collecting data. You want to do better, because that's, as you can see, this is because it's wide beam. You have to do a deconvolution really to turn that into a proper profile, and you can see there's individual strong reflectors here producing parabolic returns, which makes the whole thing look good, but the actual valid data points here don't fill the whole profile. It gets better if you use a narrow beam sonar. This is 3 degree, and this gives a profile which is pretty much good enough to use without much correction for the beam width, and you can see how it resolves the structure of a ridge where lots of blocks are piled up better than the previous one. So we always use narrow beam sonars. And then the next stage in use of sonars was side scan sonar, where we actually get a shadow picture in 2 dimensions. We don't see the central upward beam gives us the profile of thickness, and this tells us what kind of ice we're under. So here, for instance, we have 2 multi-year flows where multi-year ice looks like the surface of the moon, because you have these craters all over it, and these craters are actually the underside reflections of melt pools or previous melt pools on the ice surface, which causes the underside of the ice to melt more rapidly and leaves these the so-called under ice melt pools, but they don't usually have any water in them. Whereas first year ice looks smooth underneath. Then the best we've managed so far is multi-beam sonar, and this gives us both the 3-dimensional view. It gives us a complete 3-dimensional view of the underside. And so far we've done one big experiment on this on HMS Tireless in 2007. There hasn't been another one since, either from the British or the Americans, because there was an accident, fatal accident on board Tireless, and that's caused the Navy to be a bit reluctant to go to the Arctic again. So you put the multi-beam sonar on the bow of the submarine. This is just a couple of pictures I got of what it's like to do this work on a submarine. You get a very comfortable bunk, which is clipped to the torpedoes inside the torpedo stowage compartment, so you have torpedoes all around you. And my colleague here is Nick Hughes, who now runs the Norwegian Ice Centre in Tromsø, and you get to cuddle missiles, and there isn't much wall space to hang your Japanese print collection. There's too many bits of equipment. But one of the useful things that they will do for you is maroon you on an ice floe near a lead, and then submerge in the lead and come up through the ice, so that you can study the mechanics of ice structure interaction as the submarine surfaces. So here's a little sequence of the submarine coming up. You have to trust the captain's navigation that he's not going to come up under you. And there he is on the surface. So that's a very revealing study to be able to do. And so typically now you have multi-sonar systems working as you go. You have the upward-looking sonar, the side scan, the multi-beam, which is not shown here, and then a forward-looking sonar, which warns you of an obstruction ahead. And this is a case where an obstruction ahead did happen. That was one of about half a dozen real icebergs in the Arctic Ocean happened to be exactly in our path. And here we show passing under it. The bottom right sonar gave warning that there was something deeper than us ahead of us, and then we managed to go around it and survey it rather than run straight into it, which has happened with another submarine. So there's the deep iceberg. We've been able to do grid surveys from the submarine using it as a kind of survey vessel, and we've done this one and a closer one so that you can look at the pattern of ice ridging over wide areas. So this is what comes out of the multi-beam, and this is the best picture we now have of the underside of ice. This is from the submarine voyage. This is a multi-year pressure ridge, and we can see there's a lead running through it, joining between that and the next pressure ridge. We've got the thickness of the surrounding ice, which tells us that we're in multi-year ice, and we can see the slope angles of the ridge. We can see the block sizes of the ice blocks that make the ridge up. We can see the state of age of the ridge. The older pressure ridges are worn down more than smoother than younger ones. That's the best we can do from the submarine. We have a huge amount of data from that voyage, but the quality of data is better if you can get closer to the ice surface. And for that, we've been working in recent years with an AUV, and here you can get better quality of data. This is the AutoSub AUV cross-section through a multi-year ridge that's 33 meters deep, and another ridge nearby. And then you can still, with an AUV, you can still get enough data to be able to do statistical studies, but it's much better to get 2,000 kilometers than 200. But from the data from an AUV, here you can isolate individual ridges, determine whether they're first year or multi-year, partly from their shape, partly from the surrounding ice, and study their slope angles and the sizes of the ice blocks in them. This, for instance, is a shear ridge, and we see that there's a shear between two parts of the ridge coming out this way and this way, and with very small ice blocks in it. So this is how you do it. You cut a hole in the ice. You have a little hut where you do your work. You cut a hole in the ice and put the AUV in and program it to run under the ice, and you hope to come out at the end near your hole. And sometimes you have to make your own camp and build your own hole. So this is, in terms of data collection, this is an enormous amount of work for a fairly small amount of data, which is of very high quality, whereas a submarine is less work for more data of slightly lower quality. So here's another AUV image. This was a ridge which only formed a week earlier, so we can see that the ice blocks that were pushed down to build the ridge still haven't consolidated, and you can still see the individual blocks sticking up, and the diver that we sent down could see these individual blocks. That's a very young ridge, and this is an older ridge. This is a multi-year ridge, and you can see how it's now you have large blocks smoothed out by erosion, and with being cut in different places by intervening leads which have opened up during the years of life of that ridge. And these are younger ridges. And there's a lot of structure in the Arctic which isn't, they call them ridges, but there's nothing linear about them. And like here, for instance, you will call these ridges, and you define them as a ridge, but really they're sort of pinnacles. So the data collection that the British have done, the US data collection has been in this area called the Gore Box, which is the undeniably international waters. But the British kind of ignored that, and operated in Fram Strait and north of Greenland, and so we've collected data from kind of interesting areas, like here where you have a big build-up of pressure ridging against the north coast of Greenland and Ellesmere Island. So really the British data has complemented the American data. So that's submarines. Laser, you get a scanning lasers, which you have now, using a rotating prism, gives you something very much like multi-beam sonar, and it's quantitative as well. So you can see the top surface shape, the top surface roughness from the laser, and the bottom surface from the sonar. And we've done experiments where we've compared the two and had the laser. This is an old experiment with an ordinary laser flying over and the submarine going under. You can see the probability density functions of ice thickness match pretty well, but if you multiply the draft by if you multiply the freeboard by about 7 to get to the draft, the trouble is that 7 is not a magic number because it varies with time of year. This is the modelling of what that multiplier should be, because it depends on how much snow there is on the ice surface, because that's where the laser sees the top of the snow. It depends on the relative thickness of snow and ice, and it depends on the age of the ice. So this density function, which enables you to go from freeboard to draft, is quite a variable parameter. You can get values depending on what you use for densities and thicknesses. You can get anywhere from 5 to 9. So you have to be really careful about time of year and area of the Arctic where you're doing a transformation from freeboard to draft, or freeboard to thickness. Then next is the electromagnetic method from aircraft, and I guess Christian's going to talk about that, so but it gives you directly complete thickness, and it can be done from a helicopter or now from fixed-wing aircraft, which gives greater range. So it's possible from a number of missions now to cover quite large chunks of the Arctic. So the only thing about it is that because the reflection that's given, or the return that is taken as the thickness, comes from the first liquid water encountered, then a very young ridge, which has just formed, has a lot of water inside the ridge structure. So there is some element of loss of image from young ridged ice. Multi-year has been coming out okay because that's completely solid. You can do this to get high resolution by hauling something plastic around and putting your electromagnetic system on that. So this is a kind of hauling a kayak around the Arctic, gives you high resolution. And then CryoSat will be talked about later this afternoon, so I'll just mention ISAT. That this is the sort of you get a fairly crude rain picture here of areas that are thick and areas that are thin, and again it's because of the laser reflection and converting freeboard into draft and having a very large footprint. So satellite methods ultimately are better because they give you the whole Arctic, but there's still quite a lot of research needed to sharpen up the faith we can put in the results. And finally, a quick run through of methods. We have this method which we developed based on talking to Walter Monk a lot, and based on his measurements of waves across the Pacific and the way that long waves travel faster than short waves, and so you can detect the distance of a source. So we've done this with using tilt meters on the ice surface to measure the long ocean swell passing through the ice, and we can see that the arrival times of different frequencies. This is the period of waves measured at the site, one of the sites, against time, and you can see that a new event, a storm in the Atlantic, for instance, will give you initially long wave arrivals and then shorter wave arrivals and then disappearance because of attenuation. And by comparing these from different sites, we can see how the dispersion relation of swell in ice changes, and that is a function of ice thickness. So, and then finally, of course, we have the most accurate method, which in this case is a hot water drill. And you can spend all day and get a couple of hundred holes, but you really know that thickness and you know the freeboard. So if you want very, very accurate measurements, limited in number, that's the way to go. Okay, so that's how you do it. So what comes out, first of all, mean thicknesses, which you can get over length scales of 100 kilometers. You need at least that much to get a good average out. And we were finding and this enabled us to, in fact, in 1990 I did the first paper on thinning of the ice in the Arctic from submarine measurements, because in this region we did a cruise in 76, another one in 87, which zigzagged all over this part of the Arctic, and we could see the mean thickness, or the mean draft, was very high towards the coast of Greenland because of build-up of ridging by the mean drift towards the ice, towards the coast. In 1987 it was much less, and in fact 15% less in average thickness over this sector of the Arctic, and then by 2004 it had gone right down to less than 3 meters, so a much bigger loss. And that's what's been seen all over the Arctic, and since then, comparing data from with American data and from every sector of the Arctic, we find a big loss of mean thickness between the 50s and 60s and early 70s, which were the earliest cruises, and then the late 90s, which has got worse since then. I mean, the thinning of the ice is actually more important in terms of volume loss than the shrinking of the ice cover. So what does that loss of thickness mean? Well, firstly, if you think about undeformed ice, this is the annual cycle of growth as in Maycut and Untersteiner a long time ago. You get to about 1.5 meters in the winter, and you have a slight loss in the summer of 0.5 meter. Then it gets thicker and thicker until it gets to 3 meters. But of course today, first of all, it's not getting to such a great thickness during the winter. It's losing more in the summer, so it's coming right down. And then it's much younger ice. It doesn't have the chance to reach the thickness of the equilibrium thickness of multi-year ice. So multi-year ice, which used to dominate the Arctic in this early part of this century, red, which is multi-year, was the dominant ice type, and all through the first decade of this century, the percentage of multi-year has gone down, and it's now quite a small percentage of the Arctic ice cover. So that's partly one of the reasons, of course, is for the thinning of Arctic sea ice is a change in ice type towards first year as opposed to multi-year. But the other one is, of course, a thermodynamic change. One of the things that you do find, as in first year ice as compared to multi-year, is there's fewer ridges and they're not as deep. Multi-year ice is simply had longer drifting around to accumulate pressure ridging from lead formation followed by ridging. So here's a region of multi-year ice north of Greenland, where you can see that this is the distribution of pressure ridges per kilometre. It goes out to much greater, it ends up in fact in a much greater maximum limit, and greater numbers of ridges at all depth ranges. So we won't be getting many more of these kind of gigantically impressive multi-year ridges. Just quickly, what that means for thickness has been that this decrease in mean thickness of Arctic ice, when you multiply it by the decrease in area, which can be pretty easily mapped from satellites, you get this decline. This is for summer, and you see a much more rapid decline, more than linear, for volume of ice as compared to thickness, so as opposed to area, which seem to be declining more or less linearly. So if you now put in thickness and think about volume as opposed to area, then we get this accelerating reduction, which of course leads to predictions like this famous death spiral, where you take the volume of ice in different months of the year and for different years, and you see it spiralling in towards the centre, as opposed to being a set of concentric circles, which would happen if we didn't have losses. And also now we have thinner ice, first year ice. You find in the middle of winter massive breakup events which cause a network of leads across the whole Arctic. This is the Beaufort Sea, and we can see that if that happens, you can't really operate anymore as a scientific. When you do scientific work, you usually set up a camp on the ice, maintained by a fixed-wing aircraft using an ice runway, and ice runways are going to be increasingly unavailable in the future. So if you want to do an experiment on the ice, it's safer to cram yourselves on board a strengthened ship like this French one that was used for an EU operation, and drift across the Arctic that way instead of trying to have a camp. It's also dangerous for indigenous people hunting on featureless ice like this first year ice, winter ice in northwest Greenland, and you find in cases now of people going through the ice. So that's the first thing, is this decrease in mean thickness. But when we look now at the distribution of thickness, we find that if you take a significantly large area of the ice, at least 100 kilometres track length, you find that the probability density function of ice thickness or ice draft starts with a little peak here, which is the ice that happens to be in the form of recently opened leads. Then you get a main peak, which is the preferred undeformed ice thickness present first year or multi-year, so that can be a split peak between first year and multi-year ice, and then a tail which goes down, which is a measure of the thickness distribution of the ridges. And when you look at the tail, there's two interesting things. It's always a negative exponential in form. This is a logarithmic semi-log plot, so we see a lot of negative exponential tails here, and the slope depends on the local circumstances of deformation or thickness or growth. This is going down the east coast of Greenland from 82 to 72, and there's an increasing slope. In other words, the ice is melting as it goes down the east coast of Greenland, and there's fewer and fewer deep pressure ridges, but the distribution of the ice is still an negative exponential. And when we look at these from wherever we go in the Arctic, we find this negative exponential form. Here's four regions of the Arctic. When we look at the tails of those distributions, we get negative exponentials with a sort of excellent fit, given a finite number of data points, and the different slope depending on the local state of the ice, local state of deformation. Here's another area which has got some very thick undeformed ice, some multi-year ice. This is in off northern Greenland, and we find that the same thing happens. How does this happen? And this is an unsolved question, which I'll leave with you. We don't know why the thick end of the distribution of ice thickness is a negative exponential. We know that, of course, if you think about an isolated region, the ice thickness distribution evolves because if G is the probability density function, then it evolves because you get thermodynamic growth, you get the creation and the loss of leads, and you get a peculiar function which is called the redistribution function. We don't quite know what form that should take. So the divergence term is simply leads opening up. That means all the rest of the probability density function goes down a bit, and you get a lot of zero thickness ice, which then changes into finite thickness ice. The thermodynamic contribution is growth or melt, and the third term, which is pressure ridge production, we don't quite know what happens here. So thermodynamics injects, makes the ice get thicker in winter and thinner in summer. Divergence gives you a big delta function at zero, and everything else is reduced in frequency. and then the leads and ridges as a mysterious function which we don't understand. And that's the thickness distribution. But when we look at individual keels, that's pressure ridge keels, and count the keels, we have to use a rigid criterion for identifying what is an individual keel. But that keel has got a position and a depth. And we find that when we plot the distribution of keel depths, we find, again, an excellent fit to a negative exponential distribution. So here's a typical distribution of keel depths, and that's semi-log plot. So it's almost obscenely good fit. I mean, in geophysics, most of what we deal with when we do measurements on anything in the world is a fit to something more or less, a power law or a negative exponential, something, a fairly crude fit, a weak fit. But two really strong fits that happen in sea ice are the thickness distribution and the pressure ridge depth distribution. And the third one that's again an excellent fit is I'll go straight through to this next one, which is lead spacing, keel spacing distributions. So if you can check that out by using order statistics, where if you look at ridge drafts and you do an order statistic based on negative exponential, it will give you a straight line showing you're okay. But if you do that with ridge spacings, there's a bias, which means negative exponential doesn't work for ridge spacings. But what does work is a log normal. And you find if you do your measurements with very high resolution sonar, you get a 2-parameter log normal, which means your ridges can be indefinitely close together in the statistic. But if you have a wide beam sonar, there's a limit to how closely two ridges can be positioned, and so you have what then fits a log normal is the same log normal, but you have this third parameter which accounts for the beam width of the sonar. So using this is a wider beam sonar, and this is using a 15-meter third parameter which accounts for beam width. You get an absolutely brilliant fit to a log normal, and here using just a very small third parameter because it's a narrow beam, again you get a brilliant fit. So here again we have a problem. Okay. This is the other unsolved problem of sea ice mechanics, which I'd again like to leave with you because it's been around a long time, but I haven't seen anybody come up with a solution, which is, why is the spacing distribution of pressure ridge keels a log normal? Why is the distribution of ice thickness a negative exponential, and keel numbers as well? The keel numbers, we've got a theory basically that is, if you assume that all pressure ridges tend towards the same statistical shape, it can be a triangle, but it doesn't have to be a triangle, but the same fundamental shape, then a triangular ridge, for instance, is contributing equal amounts to the probability density function all along its length. And you can show that by working with an equivalent angle for the ridge. You can get a connection between the parameter that describes the thickness distribution of the ice and the distribution of ridge depths, and this is this parameter here. So we've reduced the negative exponential problem to one problem, assuming you can make an assumption about some kind of preferred shape for ridges. So we have one problem there: either explain the ridge depth distribution or explain the pressure, the ice depth distribution, but one gives the other. And then the other one is explain the keel spacing distribution, which hasn't been done. So I think those are a couple of challenges for theoreticians, and every other parameter in ice is weak. I mean, here's strong and weak. So the strong are these, the vector exponentials and the ridge spacings. There's a lot of weak correlations found for slope angles, keel widths, relationships between various pairs of parameters, and there's a lot of other analyses that can be done, of course. Distribute distances between ridges between leads of given widths for submarine motion, fractal analyses, and flow size distributions, which sort of obey a power law, but not a good one. So we have these weak distributions. We need to do a lot more work on them, try and sharpen them up. But I suspect that there's a random factor in ice which means that all these weak distributions will stay weak. But these two very, very strong ones, unusually strong for geophysics, I think demand an explanation and ought to get one. So I'll just end. It's very vulgar to advertise your own work, so I will. And this very week, the paperback edition of my book on the retreat of sea ice has come out and hit all major bookstores, and it's available for only £9.99. So, okay.
Any questions other than what's the price in dollars?
Peter, could you say a few words briefly about the importance of understanding porosity in all those ridge distribution and keels?
Yes, it's a good question. Well, porosity is a factor in actually measuring the thickness if you're using the electromagnetic method. But in terms of, you're thinking about water contained within a ridge or within ice.
Tons of ice.
Yeah.
Mass of ice.
Yes. What do you take as the mass of the ice? It's a good question. There's another porosity concerned with air bubbles as well, of course, and that's the main factor in this variability of the ice density that you get when you're trying to interpret laser or radar freeboard and turn it into thickness. But the water that's kind of swilling, because it's not swilling about, it's contained within the ice, and you could say that if water is really contained within the ice and new ice is growing all round it, so a new ridge is like a slag heap, a slag heap underwater. Water's permeating through it, but quite quickly the ice builds up bridges between the existing blocks, and water gets imprisoned and freezes. So even when it's still there but is imprisoned, you really maybe can say that's already part of the fabric of the ice and should be included in the volume estimate. I don't think it makes a big difference to the final numbers.
Question over here.
About the lead width distribution, I think you mentioned it was a weak correlation, but I was surprised because there was a paper by Chris Schultz a while back, and you were looking at fracture like in the outline in the mantle, and there was a nice exponential decay about the width of those spouts with the size. But like you're saying that there's no such thing like as an exponential decay, like in the number of leads.
Well, whenever we did it with the submarine, we got a power law, but the power law exponent changed. So the narrow leads had this 1.45 and wide leads had 2.5, and so when you get something like that, you start to be a bit suspicious that maybe it's not a power law, but it's something else. So it may be, yes, you may be right that by looking at more leads, you might be able to come up with a different distribution. But it's not. It doesn't jump out at you the way that the negative exponential and log normals do.
Well, Peter, it was a very interesting, informative talk. Thank you very much.